show yourself. You're on.
Hello?
Ask them if they can hear you.
Can you hear me?
Hello, sir. Hello.
Hear me?
Yes, sir.
Very
Yes.
good.
Yes. Can you hear me?
Yeah, I can hear you.
Okay, sir. Please be connected in this line, sir. Please wait, sir.
Huh?
Please be connected here.
Yeah. I'll be connected.
Okay.
I'll stay connected.
Okay, sir.
Mute it. Mute it. I've showed you how to mute. So much mute करवा दे.
It's just that I can't see the cursor. There it is.
Just on behalf of the organizers, we want to lay stress on some instructions to be followed. That is, kindly use ear and headphones for better quality of sound during all the sessions. We request you to disable your video and mute your microphone during the lecture session. If you have any question, write down in the chat box with name and email ID and wait for the moderator to respond and only then unmute yourself. If your question is not addressed in the question answer session, then we will send your questions to the speakers and their answers will be duly communicated to you. Kindly do not press on present now icon. This is very vital. You must be careful of not sharing your screen. This will disrupt the entire process. So please, very careful about that. Don't unmute your microphone and enable your video during lecture session. So please keep in mind when the lecture session will be going on. And if anyone will unmute his or her microphone or enable video or press on present now icon, the admin will be compelled to summarily remove him or her from the Google Meet. Then, if it is done inadvertently from your side, then don't be frustrated. We have nothing to do here. Please bear with us. You can follow the lectures then on YouTube.
Rahul De, please mute your microphone. Rahul De, please mute your microphone.
Not just nice. आप लोग सब बड़े-बड़े कॉपी करते हैं ना?
It's more about the shape.
Boss doesn't see what I can do with that.
हमने सिंगल मार्क सैम को ड्यूटी पे लगाया कि मैं do that.
We repeatedly lay stress on the instructions which the viewers must follow. That please disable or mute your microphone and video in the Google Meet when the session will be turned on. If you have any query or question, write down in the chat box with name and email ID and wait for the moderator to respond. Only then you unmute yourself. And also, I like to mention that if your question will not be addressed
Mute.
in the question answer session, then don't be frustrated. We will send your question to the speakers and you will be duly communicated when the answers will be received from the speakers. Kindly do not press your present now icon option. It is very, very important. You have to keep in mind, you must be careful about that. So don't share your screen. Please disable your video. Please mute your microphone when the session will be on. And if anyone will do not obeying that instructions, those instructions, then the admin has nothing to do without removing him or her from the Google Meet. The admin will be compelled to summarily remove him or her from the Google Meet. So if it will be done inadvertently, please bear with us. We have nothing to do in this regard. But don't be frustrated. You can follow the lectures, that the real-time live streaming on YouTube. So thank you all. Just after 5 minutes, we will start our session. Hello, Pallavi, Madhusudan sir. Are you here? Madhusudan sir, are you here? Professor Lokanathan sir, please unmute. Has Madhusudan sir joined?
Okay. Can you hear me?
Yes sir, yes sir.
Right.
Madhusudan, I am asking sir, is Madhusudan sir here?
Yes, sir, I'm here.
Okay. Thank you sir. Thank you.
Yeah, I can see you, I can hear you.
Okay sir. Thank you. So we are going to start at 10:30 and another topic is there, evolution of quantum mechanics, to be delivered by Honorable Speaker Professor Ajoy Ghatak. Here some instruction for the viewers or participant to be followed. Kindly use ear and headphones and please mute your microphone, disable video and don't press on present now icon. Then the admin will be compelled to summarily remove you from the Google Meet. Then you can follow the lectures from YouTube link. So that's all. Now I am entering our formal session. Then okay. Just and telling.
Okay, so start.
Okay. So just I am ready to start the session. Good morning to all of you. At the outset, I like to take privilege to present our college. I can't avoid the temptation to present our college, PRABHAT Kumar College, CONTAI. PRABHAT Kumar College, CONTAI is the oldest college of Purba Meghnad district, West Bengal, India. The torch of nationalist fervor touched the core of the magnanimous humanist late Babu Bishambar Dinda, a benevolent jamindar of the locality, and he founded the college in 1926 in the memory of his only loving son, late PRABHAT Kumar Dinda. The college that sailed as an arts college in 1926 under the aegis of University of Calcutta, initially with only 39 students, has now developed into a multidisciplinary one with roll strength of more than 7,000 students now affiliated to the Vidyasagar University. The college has established 2 research centers under the aegis of Vidyasagar University with an objective to undertake and promote sound and original research activities in the disciplines of humanities and social sciences and natural sciences, leading to award of PhD degree. In the pandemic situation due to COVID-19, the Department of Physics of this college has designed an international level webinar in the format of a series of lectures. The theme of the discussions is coined as quantum world, past, present, and future, on which a team of eminent speakers will present their valuable deliberation. These lectures help us in building basic understanding and also gaining new insights in quantum mechanics and its applications by their lucid but resourceful deliberations on concrete, real-world physical phenomena. So, before going to the inaugural session, I again like to request every participant to mute their phone, to disable their video, and with a request that the participants should not press on the present now icon. Please be careful about that. If anyone does anything within these three, these will make hindrance to the session. So, thank you all. Now, I request our Honorable Principal Sir, Dr. Amit Kumar De, to deliver the welcome speech as well as the inaugural speech for this webinar lecture series for 3 days. So, Principal Sir, please.
Sir.
Good morning, everybody. Good morning, everybody. At first, I would like to pay my regards to Professor Lokanathan. Sir, please take my corner, and Professor Ajoy Ghatak. Sir, please take my corner. On behalf of PK College CONTAI, I welcome all of you to this international webinar lecture series, 3 lecture series. Actually, pandemic area situation, we are not able to reach our students, to our teachers, to our stakeholders in a proper way. So the Department of Physics and the Department of Mathematics and some other teachers, they have generally arranged this webinar and for the benefit of our beloved student. Not only that, we are trying to our practices to adjust to the new digital system, and that's why the Department of Physics have tried to organize this webinar lecture series through webinar. And I am very much grateful to Professor Lokanathan and Professor Ghatak and the other teachers, other academicians, researchers who have given their kind consent to remain present and to deliver their lecture. And on behalf of the PK College, I again convey our actual thanks to Professor Lokanathan and Professor Ajoy Ghatak, who will deliver their lecture series today. And actually, I'm not the right person to say about topic, but I think the physics is the main pillar of this world, which quantum mechanics, quantum theory, which describe everything, the causes and the other matters. And without the development of that, we are not able to reach here. Just now, we are thinking to reach at the Mars, and that is also the legacy of the physics. So I think the lecture series will be very much meaningful and will be fruitful to our beloved student and also the teacher, the researchers, by getting to hear from Professor Lokanathan, Professor Ghatak, who are legend in the field, and I think the deliberation will give a lot of impetus to us. And at the outset, I would like to thank the governing body, the president, all the teaching and non-teaching faculty of our institution, and the beloved with stakeholders who have taken a lot of pain during the pandemic period. I would also like to all the teachers, all the respected honorable person who are associated with this lecture series through webinar. And I think there are new system we are trying to adopt ourselves. So that's why Professor Pradipta Panchadhai already briefly described everything to maintain the modalities so that we can minimize the noise, we can minimize the content, and we can get the main taste of this webinar. So please, everybody, be here with us. And with these few words, I again welcome all of you, and special thanks, Pranam, Professor Lokanathan, and Professor Ajoy who have given their valuable time to present here. Thanks to all. Again, over to Pradipta Panchadhai.
Thank you, sir. Thank you very much for such vibrant inaugural speech and your encouragement towards
in Bangalore, now called Bengaluru, to teach physics. And he, over the last 25 years, has been instrumental in inspiring hundreds of students to take to science research in general and physics in particular. I'll quickly go over a few of his academic accomplishments before I come to his association with the planetarium. Professor Lokanathan obtained his PhD from Columbia University in 1957. Later, he was a research scientist at Oxford University for about 7 years. Then he worked at IIT Delhi for a few years before moving over to Jodhpur University, and finally to University of Rajasthan in Jaipur, where he retired as Dean, Faculty of Science. He produced close to 100 papers in particle physics and high energy nuclear physics, a point which is very well known to all of you. His group in Jaipur collaborated in experiments at CERN, Geneva. Now, apart from his research in particle physics, he is a great teacher, is very well known again. I'm saying the obvious, and he has inspired generations of students to do science. His work at the Center for Development for Physics Education, alongside Professor Babulal Saraf and others at Jaipur University, Rajasthan, is very, very well known, and has benefited a number of institutions and individuals, and among them, our planetarium is one such. Professor Lokanathan made an important decision to spend his post-retirement period in the calm and sleepy city of Bangalore. It was known as pensioners' paradise in those days. With the fortunate coincidence that Professor Lokanathan settled down in Bangalore and his world line coincided with that of Professor C.B. Vishweshwara's. Professor Vishweshwara is the founding director of Jain Planetarium, and he is very well known for his fundamental research on black holes, which led to the direct detection of gravitational waves a few years back. So Professor Vishweshwara met Professor Lokanathan, and rest is history, as they say. And Professor Lokanathan was brought down to planetarium, where Professor Vishweshwara started the program called Research Education Advancement Program for undergraduate students. And Professor Lokanathan, along with Professor Bala Iyer, another renowned general relativist, have been teaching in this program since 1995. And these sessions, I must say, have been the most inspiring ones. And I have been part of this program both as a student sitting in Professor Lokanathan's class and as well as somebody who has been taking care of this program. And I must say that his way of teaching physics was something that I had never experienced before I attended these sessions. He taught electrodynamics, quantum mechanics, classical mechanics, mathematical methods, and anything that students wanted to learn from him. And not surprisingly, his style of teaching was a very big hit with all the students, and they enjoyed his teaching in the non-formal atmosphere, without having to worry about completing the syllabus or setting up question papers. I think both students as well as Professor Lokanathan enjoyed teaching in this particular program. To him, hand over back to Professor Pradeep Panchadhyay for the next part of the program. Thank you.
Thank you, Pallavi sir. I really appreciate your introduction. So, Gautam, please remove. Champa, please disable your video. So now we like to extend our thanks to Pallavi sir, Mr. Pallavi Madhusudan,
Please
Mr.
disable
Pallavi
your
Madhusudan for excellent introduction of respected Professor Subramanian Lokanathan. We are very, very delighted. We feel very fortunate to have the two great teachers of our time, Professor Subramanian Lokanathan and Professor Ajoy Ghatak, in our lecture series in the inaugural session, that is inaugural day. So I like to hand over the microphone to respected Professor Lokanathan sir for his presentation. So please sir, unmute, and I am presenting your PPT slides. So I request you to say next after your information for one slide, then I can transit to another slide then. Okay, sir. Over to you, sir.
Good morning. Can you hear me? Can you all hear me?
Welcome.
Yes, sir.
Hello,
Yes, sir.
sir.
Okay.
Yeah.
It's okay.
Very good.
Yes, we can.
Okay.
Good morning, Principal Amit Day of PRABHAT Kumar College. I'm really honored to be invited by you and Professor Pradipta Panchadhyay, Professor Ghatak, Mr. Madhusudan, who said a lot of things, some of it exaggerated. The organizers, I'm very grateful to you. And the scholar participants, I hope what I say might be of some use to you. All right. The first slide that you see shows the title, History of Quantum Theory. In my student days in the 1940s, a long time ago, we used to have a course called Modern Physics. In fact, what this title would have been called Modern Physics. And the modern physics of those times, obviously, it's an obsolete title now. It lasted only about 25 years, from about 1900 to 1925 or so. And if it's so short, why was it such a big thing? Why did it cause such a flutter? And that is what I'm going to talk about. The next slide, second slide, the next slide shows some pictures, caricatures of Isaac Newton's. On the left side, you see a cottage. In fact, Isaac Newton did much of the planet Neptune. What happened was that one of the planets, I think it was Uranus, its motion seemed a little from the theory following the Newton's laws. Two astronomers, their photographs of England and Leverrier of France, I don't want to talk about the spectroscope, but it was, if you like, a version of the prism made into a tool. And later on, the grating spectroscopy also came into being quite a bit later. But Fraunhofer used a spectroscope to map the solar spectrum. And below, you see all the colors that Newton himself saw. But as you can see, apart from the smooth distribution of colors, you find little bits of dark, several dark lines. They are called absorption lines. And these absorption lines need an explanation, because what were these absorption lines due to? Later on, much later, they were associated with elements. The process of absorption was explained later. But even in its early days, it was obvious that these absorption lines were associated with elements, because the same lines, many of these lines would be seen in emission spectroscopy. That is to say, if you, in a Bunsen flame, if you burn some salts like sodium chloride, then you will find emission lines which correspond to the absorption lines. So obviously, these lines had to do with elements in some way. And later on, of course, we know about the explanation for the solar spectrum, but that's another story. But so it is very clear that matter and radiation were connected. And that is a very important thing for the next story. The next slide shows one of the great theoreticians, Georg Kirchhoff, who realized that if matter and radiation were connected because they exchanged energy, then they both had to obey laws of thermodynamics. By then, laws of thermodynamics had been formulated, and he produced a beautiful theorem, a great theorem, in 1860, and his theorem was this. His theorem stated that when equilibrium is reached, I will come to how practical way of doing this experiment that followed, but his theorem stated that when equilibrium is reached, then the radiation would have all kinds of frequencies, a continuum of frequencies, such that between two frequency intervals, nu and nu plus d nu, the energy per unit volume, which you call u nu d nu, the energy per unit volume depended only on the temperature at which the equilibrium is reached, and not at all how this equilibrium is reached. In other words, the matter which assisted radiation to come to equilibrium, it doesn't matter what kind of a matter. By the way, I use matter in two senses. I hope you don't mind. The pun is not intended. You can use any kind of matter to produce this equilibrium with radiation, but ultimately when the equilibrium is reached, the distribution of radiation is simply dependent only on the temperature. The next slide will show how on the left side you have a sort of a blackened cavity, and as radiation bounces off the cavity many times, it reaches equilibrium. So through the matter of the walls, the radiation reaches equilibrium. But Kirchhoff said that wall, what is it made of, doesn't matter. If you wait long enough, it will reach radiation. And this radiation could be studied by opening a tiny hole in this cavity and studying the radiation through the spectroscopes, with the spectroscopes. And that would require not merely a measurement of the frequencies, but also of the intensity of radiation. The intensity will tell you how much energy is available in each frequency interval. That was a little bit more difficult. Spectroscopy was well advanced for frequency measurement, but for energy measurement, for intensity measurement, it was a little later. That's why there was a lot of confusion in those days. But curves on the right were produced. You can see the distribution, the various curves are at various temperatures. And by the way, although the smooth curves have been drawn, it was very difficult to observe the part of radiation at high frequencies, because spectroscopy was only very easy in the optical region, and in the ultraviolet and beyond the ultraviolet, it was a little difficult. So it took its time, but still it was well measured. And lo and behold, there was a big problem. What was the big problem? The big problem, I will illustrate, I will like to quote a great physicist, de Broglie, whom you have heard of in another connection. The next slide will show you his comment. De Broglie, that's the picture of de Broglie. I don't know if the quotation is there, it doesn't matter. I will tell you the quotation. What Louis de Broglie said, that is the quotation. The quotation is, some 30 years ago, physics was divided into two parts. Firstly, the physics of matter based on corpuscles and atoms. As Newton said, if you remember, all matter was made of particles, which were supposed to obey Newton's laws. And secondly, radiation physics based on the propagation in a continuous medium. Because in those days, how would radiation be propagated? Well, there was a hypothesis of ether. That's another story. That doesn't concern us. The only thing is that radiation had no such atomicity, no such particle feature. It looked like all frequencies were possible. And if you wanted to know what is the equivalent of those degrees of freedom, you will have to account for what are called modes of vibration in that cavity. And modes means that at the ends of the walls, you'll have to have nodes. And as the frequency increased, there was no limit to the number of degrees of freedom. So, as de Broglie said, what would happen is that ultimately matter, because matter has a finite degrees of freedom, whereas radiation at high frequencies especially had unlimited degrees of freedom. So radiation was insatiable. It would accept any amount of energy, and all the energy will flow from matter to radiation, and the average energy per degree of freedom, which measures the temperature, would go to zero, because if you had infinite degrees of freedom, the average energy is zero, and the average, therefore the temperature is zero. So that is what he meant. He said, so to quote him, matter must yield all its energy to radiation of its own accord until it reaches absolute zero of temperature. Well, obviously this does not happen, because as you saw, the intensity of radiation falls off at high frequencies. It doesn't go on increasing. All right. Now, therefore, this became a very big problem. And today I'm not going to talk much about that problem. I have talked about it earlier. It was Max Planck. In the next picture, you will see Max Planck's picture. In the next slide. Next slide.
Okay, sir.
Yeah.
Okay, sir, one thing.
Yeah, that's all right. Next slide. That's it. That's the picture. That's Max Planck on the left side. Max Planck came up with the idea that at high frequencies, in fact, the energy exchange between matter And radiation is not continuous, but it comes in lumps of energy h nu. And he worked out, I think there were many derivations. First he gave one derivation, then he came up with another derivation. I don't remember 3 or 4, at least 4 derivations he gave. None of which satisfied Einstein. I don't want to go into the history of this, but Max Planck produced that magical formula which you see on the right-hand side, which you're probably all familiar. And that formula fit the radiation data, all those beautiful curves that you saw, so perfectly. Now, you know, when an experimentalist, I have been an experimentalist in my life, when an experimentalist finds that his data agrees too well, then also he's worried. You know what I mean? So poor Max Planck was so astonished at the agreement that he began to produce more and more derivations to arrive at this because if it agrees so well, there must be some fundamental reason for this agreement. So the theorists began to. Well, the next picture showed that Einstein disagreed with many of them, and Einstein, and I also show Bose, Satyendranath Bose. Well, that story I'm not going to say, but it was Einstein first, and then culminated in a great work of Satyendranath Bose, which showed that at high frequencies, radiation does not have infinite degrees of freedom, but rather radiation also behaves like atoms. In other words, radiation behaves like atoms of lumps, h nu, quanta of energy, and Einstein showed they also carried momenta. And the Satyendranath Bose's contribution was that you could work out the statistics of photons very similar to the statistics of atoms. Of course, there are differences, which he pointed out, but it was a great paper. And this I just wanted to share with you because I'm sure you will enjoy this tremendous work of Professor Bose. And the statistics is now well known as Bose-Einstein statistics. Anyway, to come back to our problem, by the way, this happened only in Bose's work was only in 1924. It was very near the culmination of the end of the life of quantum theory, which I am talking about today. But I am showing this because of its how far quantum theory reached a pinnacle of success before it had its problems. All right, the next slide I want to show you. You may think, well, take classroom physics. They always act as though black body radiation was the problem. All problems are due to radiation. Not at all. As Dirac points out in his textbook, by the way, you should all at some stage read Dirac's it was one of the greatest books of physics ever written, in my opinion, and probably in the opinion of many others. And this is what he said. You see, the point is those absorption spectra that you saw in Fraunhofer lines, they correspond to something that happens inside the atom, inside matter. Well, and therefore, matter also must have some oscillations, some degrees of freedom corresponding to motion inside the atom. Therefore, what about the heat capacity corresponding to internal degrees of freedom? Well, normally you don't seem to want them. At normal temperatures, matter behaves as though it is only composed of molecules, not of those internal degrees of freedom. So there is something that prevents those internal degrees of freedom to show up at temperature. So that also is a problem. What I'm trying to say is classical physics failed not merely in terms of radiation, explaining radiation, but also about matter. All right. Now I'm going to turn to the next topic, which is going back to history, 1900. And you may think it's an abrupt change of topic. It is not. And through an astonishing coincidence, the turn of the century, 1900, in fact, it was a couple of years earlier, 3 years earlier, 4 years earlier, there was a great discovery. In fact, there were two great discoveries. 1895 was the discovery of X-rays. I'm not going to talk about that due to Röntgen. And a year later, the discovery of radioactivity. And that concerns our topic today, because radioactivity was to play a very big part in the history of quantum theory. And that is what I'm going to talk about. And three great figures contributed to the early understanding of radioactivity. The first was the discoverer himself on the left side, Henri Becquerel. Well, the story of his discovery is narrated. I'm not going to go into that detail. It's a beautiful story, which I hope you will read. And maybe I'll give you a reference if you like later. And Madame Curie. And the third one on the right, you see him in that photograph working with his workers, with his colleagues, Rutherford. Well, Madame Curie in particular, I want to say something that made radioactivity a central figure in today's talk. Madame Curie said that radioactivity comes from an atom, one atom unhindered by neighboring atoms. So it's an atomic phenomenon. It was, by the way, she said it, she didn't make it merely a guesswork. This came from her work with uranium. She did great work with the pitch blend and all that, which I hope you'll read somewhere. But this observation was so important because it highlighted the attention of physicists from the structure of the atom itself. Hitherto, atoms and molecules were useful for constructing. Dalton had used it in chemistry, lots of people. So they were all for constructing big matter. But this discovery of radioactivity, along with Madame Curie's observation, focused attention on the atom itself. What is it? What is the inside of the atom that makes it emit radioactivity? Now, the next slide shows that even before radioactivity, the next slide, can you try the next? That's right. That's a beautiful slide of Michael Faraday. He, of course, preceded radioactivity, this, and I'm showing it to you only for one reason. He did some, he had done so many brilliant things but I'm concentrating on only one, his laws of electrolysis. That is to say, how much charge is deposited during electrolysis, and the amount of a monovalent substance deposited is now called, the charge is now called Faraday constant, 96,450 coulombs. Now, why is this important? By the way, this happened many years ago, many years before the discovery of radioactivity. Why is it important? It is important because, well, by the way, I would request all the participants to do it at home. It's a very elementary calculation. You divide 96,450 coulombs by Avogadro's number, and you will arrive at the charge of what? You will arrive at the charge of the electron. That is, the entire business of electrolysis seems to be all that happens is a certain charge in lumps of something called, which were later to be called electric charge, quantized as electron charge. That will come much later, but it was already evident from Faraday's laws. So Faraday's laws itself suggests that even electricity is associated with atomic phenomena. So with all that, the next slide will show you that atoms are now no longer to be regarded as unbreakable. The electrons must come from inside the atom. So how is the atom put together? And the next slide shows you one such model due to the great J.J. Thomson. Thomson, in fact, was associated with the discovery of the electron a few years earlier. And Thomson also was senior to Rutherford. And Rutherford worked for a short time with Thomson in Cavendish laboratory. And Thomson himself came up with the first model of an atom. And if you look up on the right, that is an amrud, a guava fruit. I am sure you are all familiar. In West Bengal, you are all familiar with guavas. You eat a lot of guavas, lovely guavas there. So what is this? Those pits that you see are like electrons embedded throughout the atom. So the electrons are distributed throughout the atom, negative charges. So although the atom as a whole is neutral, the positive charge is distributed throughout and the negative charges are distributed as lumps of electrons embedded in it. This was his model. Now the model is obvious, but turned out to be wrong. Well, turned out to be not tenable for various reasons. But before I do that, I should also tell you Thomson had made some very great contribution apart from this. Thomson, by other methods which I don't have time to go into now, through scattering, he was able to determine experimentally how many electrons would there be in each atom from Thomson scattering. And that was of great importance because later on, Thomson's work, along with a person whom I'll talk about called Moseley, they determined that the atomic number was simply the number of electrons. And Thomson's work had a great deal to do with it. Anyway, that will come later. But right now, the next slide shows you the Rutherford. This picture, you may wonder why I am showing this picture. I am showing this picture because in the middle, you have the beginnings of today's CERN and Brookhaven on all those accelerators. And here you have an accelerator in between Rutherford and his colleague Geiger. And what is the accelerator? The accelerator is a natural one called polonium. A polonium emits an alpha particle at an energy of about 7 MeV or so, and those polonium particles are nature's way of producing an accelerator, which Geiger used for his famous experiment. And I am showing this to you for a very important reason. It is not a joke. It is an important reason because today's accelerators, or if you like, they are simply aping this Rutherford's, Geiger's way of studying atoms. And all right, what did Geiger do? Well, Geiger let it fall on gold foil and then produced results which Rutherford, I am not going to go into this. Rutherford then explained this in terms of an entirely different model. the Rutherford model of the atom. The next slide would show, that's right, the next slide shows that scattering, and from the right in the middle, you have a slit passing through in which there's a gold foil, and you have large angle scattering of alphas, and from which Rutherford worked out, it's a theory which is not very difficult to work it out, but the sum total of all that was that Rutherford was able to show, next slide, that the next slide will show Rutherford model. Rutherford model is simply that the atom is not at all like a guava, but instead it is more like a solar system instead of a solar system in an extremely small scale. Instead of the sun, you have the nucleus, and instead of the planets, you have the electrons going around. Very good. So it's a planetary model, if you like. And it's not just a planetary model, because the law of attraction, of electrical attraction, is more or less the same as the law of attraction of gravitation, namely 1 over r squared. The force is proportional to 1 over r squared. Therefore, the orbits are also very similar. So you may say that, so what? Well, we'll come to that later. In fact, it's very misleading to think that it's merely like a solar system, as some of the textbooks say this, but there's a very big difference which I will come to later. But right in the beginning, it is already difficult to see how this atom is sustainable. Why? Because unlike, well, now you have gravitational waves, I shouldn't say this, but now, if already charges going around in circles like that, it was well known that such electrical charges going around will radiate energy, and if they radiate energy, they will soon collapse. Instead of going around to a bigger circle, they will spiral into a smaller and smaller circle and collapse into the nucleus. So the atom cannot be stable unless you invoke some law to prevent it from collapsing. That is why we are talking about it today, because quantum theory was all about how to stop this. All right, the next slide shows you that spiraling thing I talked about just now. And let's go to the next one. The next slide. The next slide shows line spectra. Now the line spectra associated, these line spectra are also suggestive that something is happening in the atoms associated with these line spectra. Now what? Now let's face it. What would occur to us? What is the similarity? The similarity is like a musical instrument. You have a musical instrument, you blow on it, you find not merely a sound, a beautiful tone, but you also hear some overtone, some harmonics, etc. They come. So you think that some kind of oscillations are taking inside these elements, and these lines correspond to the harmonics. The only difficulty was these harmonics are not spaced in the way that a musical instrument, the harmonics are spaced. They are very different, and that had to be explained. So here was spectroscopy far ahead of theory, waiting for a theory. And along came, now the next slide, the big man who was going to produce a theory in 1913. This is Niels Bohr and his family. Well, the reason I'm showing his family was, it turns out that his brother, Harold Bohr, was himself a great mathematician. His son also won a Nobel Prize, Ajoy Bohr. That's another story. In fact, I myself had met him once when I was a student. That is Niels Bohr's son. So it's a very distinguished family. But Niels Bohr was in 1913, he was a postdoc working at Manchester under Rutherford, and he produced his great theory. Well, you are probably many of you, next slide. Bohr, of course, said that he used his Rutherford model to come up with the theory, and he had to explain two things. The first thing was, why are there orbits which don't collapse? Number one. Number two, where do these lines come from? Where does a particular line come from? A particular frequency come from? So these are the two things that are necessary to be produced. And unlike the solar system, in the case of an atom, think of this. In the case of a solar system, you have, well, a finite number of planets, certainly less than 10 major planets, and the radii are more or less haphazard, and the radii are, well, what they are because of the way originally they split and went into orbit cosmologically. On the other hand, in the case of the model of the Bohr's model of the hydrogen atom, hydrogen was the one he first concentrated on, hydrogen atom, all the orbit, if you take a thimble full of hydrogen, it would contain up 10 to the power 23 atoms or something, and all of them have the same line spectra. So they have the same orbits, obviously. Unlike the solar system, you must have some reason to explain why 10 to the power 23 atoms have exactly the same kind of orbits. So that required attention. So you're all familiar with those two laws. Next slide. So he produced, I am giving this quotation, he said about helium, which we can skip this slide. Next slide. So, according to Bohr, the only role of the nucleus doesn't do anything, by the way, at this energy scale, but it only produces a force, just like the sun does. On the other hand, the orbits are restricted by a quantum rule, which you're familiar with. Next slide. So unlike the solar system, you have 10 to the power 23 atoms, I've said this, and therefore the orbits are all fixed according to his quantum rule. And then when one orbit jumps in, when the electron jumps from one orbit to another, it does like what a tuning fork does, it produces a line, and that line gives you the particular frequency. But unlike the tuning fork producing harmonics, well, a tuning fork is a fairly pure instrument, but many other musical instruments produce harmonics. Unlike that, these various lines are not harmonics of a fundamental in any simple way. Instead, they obey a different rule called Ritz combination. I'll come to the next slide. The next slide shows that these stationary atoms cannot be explained except with the quantum rule. And the next one, we'll go to the next one. All right. So Bohr's new idea is that it is when the quantum rule is obeyed that the angular momentum has to be well, I won't go into the details of the theory. When you produce this quantum rule, it restricts the orbit to certain orbits, and when it jumps from one orbit to another, then it emits a photon, and the photon has an energy h nu. All right. Very good. And if you divide on the bottom, you have h nu equals the difference in energy. But if you divide the equation by h, then it gives you the frequency. And lo and behold, if you write the equation in terms of the frequency, it will easily explain what is called the Ritz combination principle. The Ritz combination principle said that although the frequencies are very strange compared to the harmonics of a musical instrument, they obey a very beautiful relation that if two frequencies are produced, their combination frequencies are also produced. I won't go into the detail, you will find it in textbooks. So this is a very easy explanation of Ritz combination principle. That was one of the great successes of Bohr. But the big success was that he could arrive at the energy associated with these orbits in terms of his Bohr formula. I hope the next slide shows the Bohr formula. I don't know if it does. Well, anyway, Bohr's formula is in terms of a constant called Rydberg constant. And the Rydberg constant in the Bohr formula, the Rydberg constant is related to all the known constants. Planck's constants, velocity of light. It does not require any new constants. So it was one of the greatest successes because it didn't require any new constants to arrive at his idea. And Einstein said, in that case, this must be a great theory. I am quoting Einstein. All right. So these are the two great successes. It also easily explains Ritz combination principle. The next slide. That's Bohr's formula. And as you can see, that big R is what I'm talking about. The big R contains, on the right-hand side, it should read twice pi e to the power 4 times the mass of the electron divided by h cubed. It contains nothing at all other than known constants. So it's a remarkable formula, and that is the remarkable success of Bohr. All right, let's go to the next slide. In the next slide, in fact, not merely was it successful with hydrogen, but it was successful in explaining spectra associated with ionized helium. That's a beautiful story. I don't want to go into the detail. It only required a minor adjustment. The mass was not quite the mass of the electron, but the reduced mass. And spectroscopy was so accurate that that reduced mass also can be deduced and compared with Bohr's success. It was such a great success, and that is why Einstein said, then this is one of the greatest discoveries ever made. I'm quoting Einstein at the bottom of your slide. Next one. And all right, we can skip this. The next slide. All right. Now, in spite of all that, in my view, the greatest success of the quantum theory, in my view, was to come later, was to understand the periodic table. At least the sketch of the success of the periodic table already came with Bohr and Stoner. And it was in the a little later than 1920. Bohr had an initial idea, but Stoner had formulated it clearly, and I think Stoner's paper was dated 1924. And what was the idea? Now, to explain this idea, I must go back a little bit about how beautiful spectroscopy was. Spectroscopists had found a strange thing, that the spectra of hydrogen and the spectra of lithium and the spectra of sodium, they could be matched in a way as though you simply translate the entire set of spectra towards a higher frequency, and they one set of, well, the helium spectra and the lithium spectra and the sodium spectra could all be matched. This meant there must be some similarity between these structures. What is the similarity? Now, by then, you remember what I said about Thomson and J.J. Thomson. He knew how many electrons each element had, roughly. A more precise X-ray work by Moseley, in fact, determined that the atomic number was just the number of electrons in the atom. And evidently, the number of electrons in sodium was much more, and lithium was more than the number of electrons in hydrogen. And yet the spectra were the same. Why? Because they came to the conclusion that only one of the electrons in lithium and one of the electrons in sodium really play a part in producing these spectra. So the others form what are called closed shells. So, in other words, the periodic table could be built up. And in German, it was called the Aufbau principle, building up principle. So this was a great idea, and it of course required the genius of Pauli also to say why you cannot put more than a certain number of electrons in each shell and things like that. That's another story, Pauli's principle, how that came into being. But all this gave a beautiful qualitative, at least a qualitative understanding of the periodic table, and to some extent a quantitative understanding also. And in my opinion, the early quantum theory already had a very, very nucleus of a great success. All right, if that is the case, why were people unhappy with it? All right, the next slide. So the next slide, can I have the next slide? All right. The strange rules are easily, these are the successes. Its combination privilege also explains, by the way, it explained Bohr's orbits, explained the magnetic properties, including normal Zeeman effect, etc. And if you, by the way, you can try estimating the amount of the magnetic field at the center of, say, a hydrogen atom due to the electron motion. It's huge, and that produces a sort of, these are all things which are successes of the Bohr model, and the word Bohr magneton still survives. Next slide. All right, what are the failures? The quantization rule of Bohr seems ad hoc. It doesn't, well, you just state it more or less. You don't have a systematic logic to it. All right. The third point line there, it says the emission and absorption processes were not understandable. What do I mean by that? In fact, Rutherford himself had commented on it. He said, when an atom in a Bohr orbit when an electron in a Bohr orbit jumps from one orbit to another, it emits a photon. And Rutherford said, how does it know which orbit to jump into? And when does it emit this photon? At what place? In the middle of the change? In the beginning? At the end? When does it emit? It had to be in one go because it's a lump. H nu. And if that is the case, it cannot conserve energy. You can convince yourself, because in between there will be a non-conservation of energy. This was a very big problem, that in that case, conservation of energy in atomic phenomena cannot be explained very easily, and you had to bypass it. In fact, there were even attempts to bypass it for some years. I wouldn't go into that. So these are all the failures it wasn't very clear. And the last line says, the intensities of lines of these spectra were also not very easy to, well, Bohr did come up with some ideas, but they were not very, very precise. And the intensities of these spectra could not be explained very easily either. And these were all very big failures. As it turned out, this was in fact precisely the beginning. The Ritz combination principle and how the intensities are to be produced and how the electron jumps from one state to another, connecting two states. These were the ideas that Heisenberg really used in a very brilliant manner to produce his new quantum mechanics, which others will talk about, but I will not. What I'm trying to say is all this happened. 1924 was this Stoner paper on periodic table. By 1925, Heisenberg had come up with his quantum mechanics, the first paper. 1926, Schrödinger came, others will talk about it. So the great happy life of quantum theory lasted 25 years, 1900 to 1925. I have not even talked about the great work that de Broglie had done a little earlier than 1925. He had suggested the wave particle duality. That also had to be explained. So these are all things that quantum mechanics had to do. So to sum up, what I want to say is the great ideas of quantum theory are not small successes. They still last. Only thing is they've been supplanted, it's true, but we still use Bohr theory to have a qualitative understanding of many things. For example, the one great thing I want to tell you, that Schrödinger gave a beautiful lecture around 1945 or 46, I don't remember. And it's available in a small book. I hope it's available for you people. You can consult it. It's called, this follows a series of lectures he gave. The title is, What is Life? Life, L-I, Zindagi, L-I-F-E, life. What is life? And what Schrödinger said was that the idea of a gene, what we now know gene, cannot even be conceived in classical terms. Why? Because the gene is something that passes on from one generation to another, practically unchanged unless there's a mutation. So in other words, everything even in biological world is more or less stable except when it is muted. So these small changes are not allowed. For example, why is there a periodic table? A periodic table of days 92 elements. Why only 92? Why is there not a continuum of matter? Why is there not something that goes from carbon to nitrogen in a continuous way? Something that is slightly more carbon, slightly more nitrogen. There's no such thing. It's either carbon or nitrogen. Why? All these things are, in fact, the successes of already a Bohr early quantum theory. So one should not minimize the great influence of the early quantum theory. And if it has been supplanted, that's all right. That today, the quantum mechanics, on the other hand, of course, is still surviving and is continuing very well, and others will talk about it. So that was what I wanted to say, the early quantum theory, beautiful quantum theory, which we remember had its time. Thank you very much.
Thank you very much, sir. So much Thanks and regards to you for such a mind-boggling lecture. It was a thrilling experience for us. It was like a smooth voyage in the ocean of quantum world. So, just I request some questions from our organizers. They already assembled it, I think. Please send to me. Just one question, sir, in my hand.
Yes.
That. Hello.
Yes.
Hello. Subhendu Kandar. Hello, Subhendu Kandar. Can you hear me, Subhendu Kandar? Can you
Yes,
hear me?
sir. Yes, sir.
Just unmute and ask
Sir,
the question.
sir, actually, Heisenberg uncertainty principle has it is applied in the quantum physics. Does the Heisenberg principle only apply to quantum mechanics for quantum physics?
Let me ask, are you asking, is it applicable only for small things or big things? Is that the question?
For big things.
Well, it is all, in principle, you can apply it to big things also. For example, let me take an example. The wavelength is related to momentum as lambda equals h over p, right? All right. Now, what is p? I am here, Lokanathan sitting in his chair. His momentum is huge because his mass is huge. Even if he vibrates a little bit, his momentum will be huge. So the wavelength will be so short, so you don't feel any wave effects, right? So what I say is, it is not that Heisenberg's uncertainty principle should only apply to microscopic objects. It is a general law, but it is only in microscopic objects that it shows up easily for us to observe. It is not because it doesn't hold in higher things. On the other hand, of course, how to interpret the uncertainty principle, that is a different story. The interpretation of Heisenberg's uncertainty principle is a complicated affair, and even to this day, there are people who disagree with this, but that's a different question. The question that you asked, I hope I say unambiguously, Heisenberg did not mean it only applies to microscopic. The point is that it's only in microscopic entities that you can see it, you can observe it. Right.
Okay, sir. Thank you. Right. Now I want to take another question from Sumande. Sumande, please unmute yourself. Sumande.
Yes, sir. I can hear.
Yeah. Is there any experiment to prove that gravity and quantum mechanics can be reconciled? Sir, yes, can you hear? Is there any experiment to prove that gravity and quantum mechanics can be reconciled?
Yeah. Well, first let me say, my first answer is that I am not at all the person who is capable of answering this. This is an outstanding problem to this day amongst great theoreticians. In other words, it seems, I am told, and by the way, I am almost like you in this particular case. In other words, the unification of the fundamental forces is apparently reasonably possible in all other cases, but it is very difficult to include gravitation also, to be included in the unification of all the forces. Why this is a technical matter which I can't go into, maybe others can answer, but the answer, the only thing I can tell you is to this day, it has not been successful. That much I know.
Yeah, sir. Thank you, sir.
Yeah.
Thank you, sir. We are running just time. It is the time of Professor Ghatak now. It is the turn of him. So, at the end of the lecture of respected Professor Subramanian Lokanathan, we are simply amazed. And again, I like to mention that we feel very lucky to have him here today. I wish his good health and long life, and also continuing versatile work in the field of physics. So, sir, again, thank you, regards to you, and heartfelt gratitude to give us your kind consent at this age. So,
Thank you very much.
Keep safe. We will be happy, and we want to see you in future.
To hear.
Yes, sir.
Online to Professor Ghatak.
Professor Ghatak turns here. Now, sir, please, Professor Ghatak, sir, please unmute yourself, sir. Hello, sir. Hello, sir. Hello.
Yes, I can hear.
Okay, sir. Just another session. Here, the speaker is, sorry.
So can I start?
Sir, 1 minute. One minute, sir, please. Now, for this session, I like to introduce Professor Ajoy Ghatak. You are seeing on the screen Meghnad Saha Professor, the National Academy of Sciences, India. His topic of deliberation is evolution of quantum mechanics, and all of us know that he was the formerly professor of physics department, IIT Delhi. So just for a brief introduction, I feel happy to introduce him before you with some sentences quoted here. Ajoy Ghatak is currently Meghnad Saha Professor. As I have mentioned, he received his BSc from Agra College, MSc from Delhi University, PhD from Cornell University after a research associateship at Brookhaven National Laboratory. He joined IIT Delhi in 1966. Professor Ghatak has research interests in fiber optics and quantum mechanics. He has authored several books, including his undergraduate text on optics, which has been translated to Chinese and Persian. His other books include Quantum Mechanics, Theory and Applications, co-authored with Professor S. Lokanathan, Fiber Optics, Lasers and Optical Electronics, all three co-authored with Professor Kosturirangan Thagarajan. And his most recent book is on Einstein's Year of Miracles, E equal to mc square, the light, quantum and special theory of relativity. He is a recipient of the 2008 SPY Educator Award in recognition of his unparalleled global contributions to the field of fiber optics research and his tireless dedication to optics education worldwide. The 2003 Esther Hoffman Baylor Award instituted by OSA, Optical Society of America, in recognition of the outstanding contribution to optics education. International Commission for Optics 1998 Galileo Galilei Award, and also the CSIR 1979 SS Bhatnagar Award for outstanding contributions in physical sciences. Very recently, he received the OSA, Optical Society of America, and Optical Society of Korea San-Soo Lee Award for his seminal role in the development of fiber optics and guided wave of photonics, and for pioneering optics education in India. So, sir, we are lucky to have you at this seminar, and you have given us your kind consent at the first time when we approached to you. So it's our luck to have you here. So, sir, please proceed, and over to you. Just start your presentation, sir, please.
Thank you. Thank you, Pradipta.
Okay, sir.
Can you hear me?
Yeah, yes.
You can hear me clearly. Can you see the slides on the screen?
Yeah.
Is it now visible, the slides?
No, sir.
No, sir.
No. It is now not visible.
Just 1 second. So it says that I can't share your screen. So let me see. It's present now.
Present now.
And just 1 second.
Yeah, it is coming, sir. Please full screen. Press F5 or go to slideshow. Then click on the.
Can you see the slide?
Yes, sir. Sir, slide is visible, but please press it. Press on the full screen mode.
It is now in the full screen mode. Can you see?
Okay. Yeah, visible, sir, in full screen mode. So please start.
Okay. Thank you, Pradipta. Thank you very much for organizing this webinar. I'm going to give you a simple talk on evolution of quantum theory. We just heard a very beautiful talk on the history, and what I'm going to talk to you about is a little textbookish thing. Evolution, wave-particle duality, and evolution of quantum theory. I thought I will mention that both Professor Lokanathan and I were taught by Professor D.S. Kothari and Professor R.C. Majumdar at Delhi University. They taught us quantum mechanics and nuclear physics at Delhi University. I studied during 1957 to 59. That was long time back. And Professor Lokanathan had studied from them a few years before me. And here is a photograph of myself with Professor Daulat Singh Kothari and Professor Ajit Ram Verma, who was a great solid-state physicist. And I also had the privilege of learning quantum mechanics from Professor Hans Bethe at quantum mechanics at Cornell University during 1960 to 62. He was a great teacher. He lectured on basic quantum mechanics, which was really a very beautiful set of lectures. And then he had a course on intermediate quantum mechanics. In fact, he has a book also on intermediate quantum mechanics. And as you all know, Hans Bethe got the Nobel Prize in Physics for his work on astrophysics. And here is a photograph of myself with Professor Lokanathan when we were much younger at IIT Delhi. So this, as you all know, this webinar is coordinated by Dr. Pradipta Panchadhyay, and I congratulate him for all the efforts that he has put in coordinating this webinar. And such webinars, in my opinion, go a long way towards the development of science and technology in India. And as was mentioned by, I had a slide, but I forgot to include that, by Mahendra Lal Sarkar in 1869 or something like that, 1869, that to remove the poverty in our country, science and technology should develop. And today, even today, 30% of the population is below the poverty line. So that is a staggering 400 million people. Even if it is not 400 million, at least 200 million people are definitely below the poverty line. And we can remove the poverty only through science and technology and education of women. So therefore, all such efforts need to be appreciated. And I'm very grateful to Dr. Pradipta Panchadhyay to organize this seminar and to such seminars. As I will give you some references to some outstanding textbooks on quantum mechanics. The first one, as was mentioned by Professor Lokanathan, is by Professor Dirac. That is a classic book. And Professor D.S. Kothari had taught us from that book only. And then the Feynman lectures. And as someone has written, Dirac's articles are like poems, but they do not contain figures. And then there is a book on quantum theory by David Bohm, beautiful book. And David Bohm is considered as one of the great authorities in quantum theory. And then there is a book by Cohen Tenuji and his collaborators, which has been translated by two of my very good friends, Nicole and Dan Ostrowski. So here is a photograph of 1962 photograph of Dirac with Feynman. I thought it was a very beautiful photograph. And I think they were discussing physics at that time. And in the center, we have the photograph of David Bohm with our own spiritual guru, J. Krishnamurti. And in this photograph, you have Cohen Tenuji receiving the Nobel Prize. And here is Nicole and Dan Ostrowski, who are my very good friends who live in France, who translated the book by Cohen Tenuji. What I will discuss today is more or less given in our quantum mechanics book, which I had the privilege of writing with Professor Lokanathan, and the 6th edition, which came out last year. And also my book on optics. I have now a chapter on what I'm going to talk today. And hopefully the 7th edition will come out soon. And then I have written a small book for school students, class 12 students, on Einstein's Year of Miracles, when he introduced the famous equation E is equal to mc square, the concept of the light quantum, and the special theory of relativity. Ever since man could see, he has been wanting to know what light is. And here is a sadhu worshipping the light from the sun. And Isaac Newton, in his famous book on optics, said that are not the rays of light very small bodies emitted from shining substances? So he had put forward the corpuscular model of light, and using that, as you all know, he derived Snell's law. And of course, many people feel that the corpuscular model of light was put forward much before Isaac Newton. In fact, by René Descartes, had also used a corpuscular model of light to derive Snell's law. But the reason why corpuscular model got accepted was because Isaac Newton had propagated that in his book, and his book was very famous. And also because light can propagate through vacuum. A wave requires, as you know, a medium. So here the space between the sun and the earth there is nothing there. So how could light propagate? So it must be a corpuscular model. And the fact that light almost travels in straight lines. Here is a photograph of a man on the moon. And sorry, what time is it? I must not speak for more than 1 hour. This is 12:10 approximately. So notice because he is on the moon, and because moon has little atmosphere, so there is the sky even in the daytime looks dark, and the shadows are perfectly dark. And this photograph shows that light almost travels in straight lines. And of course, if you sit in a shadow on the surface of the earth, you can read a book, as I've shown in this slide, and that is because of scattering. There are air molecules, hydrogen, oxygen, nitrogen, which scatter the light and allows you to read a book even in a shadow. But if you are sitting on the moon, you will not be able to read a book in your own shadow. So therefore, the shadows are perfectly dark on the surface of the moon for two reasons. Light travels in straight lines, and also that there is no atmosphere. There is very little atmosphere on the surface of the moon. Then around 1650, Christian Huygens put forward the wave theory of light in his famous book. But this was at the same time as Newton, so no one really believed in the Huygens wave theory because Newton had such a dominating personality. It is said that everyone believed in Newton much more than Newton believed in himself. So what is a wave? The simplest wave is if you hold a string and make it move up and down, you generate a wave. And this is an X-polarized wave because the displacement is in the X direction. And the displacement is given by this equation, A cos kz minus omega t. And this equation represents a wave. So whenever you get this from physical consideration or from the solution of a particular equation, then you can predict the existence of waves. And often we write this as we use the exponential notation. And because it makes it easy to do some calculations, as you all must be knowing. So I can write this expression as, I can take the k out and write this as z minus vt, where v is defined to be equal to omega by k. So that if at t equal to 0, it is a cos kz, then the whole thing gets displaced by a distance v delta t in time delta t. So therefore, this tells us that if I have an expression like this, it represents a propagation of a disturbance which moves with a velocity v, which is given by omega by k. So the whole string, the displacement, not the string, the displacement moves by a distance v delta t in time delta t. So therefore v, which is defined to be equal to omega by k, represents the velocity of the wave. And of course, k is equal to 2 pi by lambda. So if you have a calm pool of water, and if you have a sharp needle moving up and down, then it generates waves. And I'm sure you have seen that on a calm pool of water. And if you have two such needles or two such sharp devices which are moving up and down in phase, each will send its own set of waves which will interfere. So if one produces a displacement a cos omega t at a particular point, and the other produces a displacement minus a cos omega t, then according to the superposition principle, the resultant will be 0 and you will obtain a minimum. So interference leads to maximum and minimum intensity, which today you learn at the high school level. So this is an actual interference pattern, photograph of an actual interference pattern produced from two sources point sources vibrating on a calm pool of water. So although the wave model of light was put forward around 1650 by Christian Huygens, it could be experimentally demonstrated only around 1801 when Thomas Young carried out a very beautiful experiment. He allowed monochromatic light, and he produced monochromatic light by passing the sunlight through a filter. And then he allowed to fall on two holes, and he obtained straight line interference pattern, almost straight line interference pattern. And he could say because that is the interference pattern which you study in your school, and if you calculate the distance between the two consecutive fringes, that is the fringe width, which I denote by beta. Small d is the distance between the two holes, and capital D is the distance between the two screens. I can calculate the wavelength. Thomas Young did that, and he said that visible light has a wavelength of half of a micron, half of a millionth of a meter. And that is why interference experiments are difficult to perform, because the wavelength of light is extremely small. But he could establish that light plus light could produce darkness. This is a quotation of Max Born. I want to mention here one thing, that the original Thomas Young's experiment is not a double slit experiment, it's a double hole experiment. So you get straight line interference pattern using two tiny holes. So this is the two-hole famous Young's double slit experiment. So this figure I have taken from the Feynman lectures, in which he showed that there is a gun emitting bullets, corpuscles. And so the corpuscles, these tiny bullets reach this detector either passing through hole number 1 or through hole number 2. So if P1 is the intensity distribution when hole number 1 is open, and P2 is the intensity distribution when hole number 2 is open, then when both holes are open, the bullets will pass through hole number 1 or hole number 2, and you will get the sum. That is, the bullets will either go through hole number 1 or hole number 2. So therefore, if light is represented by classical particles, then those tiny particles will either pass through hole number 1 or hole number 2 and will not demonstrate interference. So therefore, the very fact that we get interference and light plus light produce darkness cannot be explained by the means of a simple particle model of light, and so therefore light was indeed a wave. And very soon, within 10 years or so, there were many experiments done by Fresnel, Arago, and other people, diffraction and interference, that the wave theory of light was soon established. In fact, there is a very beautiful book by Andrew Robinson. He describes Thomas Young as the last man who knew everything. He was a great physicist, medical doctor, and he knew everything at that point of time. So the main question that started bothering scientists was, as you all know, that light was a wave. You could do the diffraction experiment, you could do interference experiment, but how could it then propagate through vacuum? Because a wave, like a sound wave, requires a medium to go from one place to the other. And as we all know, the ether, concept of ether was developed, and we now know that the ether does not exist. So I will not go into the details of that. Around the same period of time, the laws of electricity and magnetism were getting developed, and Michael Faraday discovered the Faraday's law, according to which a changing magnetic field produced by an oscillating magnet produces a current. And Maxwell put that in the form of Maxwell, or some people say Oersted, have put forward these equations, but they are now in the book by Maxwell. So Faraday's law was known It was an experimental law. Maxwell put that in the form of a vector equation, which you know as curl of E is equal to minus delta B by delta T, which physically implies that a changing magnetic field, if you have a changing magnetic field produced by something like an oscillating magnet, then it produces an electric field. Then we had Ampere's law, or Oersted law, according to which if you have a current carrying current, then it produces a magnetic field. And Maxwell put that in the form of a vector equation. These are experimental laws, therefore. Faraday's law and Ampere's law are experimental laws. Curl of H is equal to J. They cannot be derived. So, what Maxwell did was a remarkable contribution. He said that not only a current can produce a magnetic field, but he said that because you see, a changing magnetic field produces a changing electric field. And so therefore he said that changing electric field will also produce a changing magnetic field. And therefore he added one more term. Initially we had Ampere's law. So he added the delta D by delta T. And we now call this as a displacement current. And he justified the use of this introduction of this term by making this equation consistent with the equation of continuity. I will not go into the details, that is part of electricity and magnetism. So he introduced the concept of displacement current, that not only a current, a conductor carrying current produces a magnetic field, but a changing electric field, like between the plates of a condenser when it is charging, that also produces a magnetic field. So in free space, for example, the Faraday's law is given by this, and modified Ampere's law, in which you introduce the displacement current, is given by this. So then you can show that an expression, a wave-like equation like this, satisfies both equations. So therefore, if you substitute this, a wave-like solution, in the first equation, when you take the curl of this equation, integrate with respect to time, and divide by mu0, you will get this expression further. And then you substitute both these expressions in the second equation, then you will get omega by k equal to 1 over mu0 epsilon 0. And from the values of the constants that were available at that point of time, he found that omega by k should be about 300 million meters per second. So therefore, understand what Maxwell tried to do. He put the laws of electricity and magnetism in the form of equations. He wrote them down in free space, and he said that waves are solutions of this equation. This equation, as I tried to tell you before, is an X-polarized wave. And the corresponding magnetic field is given by this. So wave-like expressions for the electric and magnetic fields are solutions of the laws of electricity and magnetism. And so therefore, he predicted, understand this carefully, he predicted around 1860 the existence of electromagnetic waves. And from theory, he said that the electromagnetic waves must exist whose velocity is about 300 million meters per second. And this value was close to the value of speed of light that was measured by Fizeau in 1849. And he said that these two numbers cannot be accidentally equal. And so therefore, light must be an electromagnetic wave. So, as I tried to show you, an oscillating electric field produces an oscillating magnetic field, and oscillating magnetic field produces an oscillating electric field. And it is the concept of, I must mention that the concept of fields was introduced by Michael Faraday. That a charge sitting in vacuum produces a field. Today we take the concept of field to be granted. It's a very profound concept. It produces a field, so that if I put another charge there, there will be a force of attraction or repulsion. So whenever you produce light, associated with the light beam, there is an oscillating electric field. The oscillating electric field produces an oscillating magnetic field at right angles to that. And then as oscillating magnetic field produces a oscillating electric field, that is how the fields propagate in vacuum. And the fields and the electromagnetic waves carry energy through vacuum. And that is what the famous Maxwell's electromagnetic theory is. So around 1864, Maxwell predicted, that is the most important word, predicted the existence of electromagnetic waves, because he said that the wave-like equations are solutions of the laws of electricity and magnetism. And because the two values, the velocity of the electromagnetic waves was very close to the experimentally determined value of the velocity of light, so he could say that light itself, that these two numbers cannot be accidentally equal, and that light is and itself is an electromagnetic wave. This is said to be one of the greatest syntheses. When you have two fields brought together, that is a synthesis. So electricity and magnetism and optics were two different branches, and he synthesized them. That was the great work of Maxwell. So that was one of the greatest syntheses in the development of science. And one could say that God said, let there be Maxwell's equations, and there would be light. Then in 1887, within 20 years, Heinrich Hertz, as you all know, generated electromagnetic waves of much smaller frequency than that of visible light, and got it reflected by an aluminum screen and generated standing waves, measured the frequency and wavelength, and calculated the velocity and found that that was equal to about 300 million meters per second. So Maxwell electromagnetic theory, there is one more experiment that I would like to tell you, that here is a glass prism in which a light beam undergoes total internal reflection. And if you put another glass prism with the air gap in between, then the beam undergoes what is known as frustrated total internal reflection, and a small part of the beam can tunnel through. And this comes from Maxwell's equations. This is classical wave theory. And it was around 1894, our Indian physicist Jagadish Chandra Bose, I thought the younger generation, I'm sure you all being in West Bengal, you will know this. Jagadish Chandra Bose was the first to demonstrate optical tunneling using millimeter waves. And these are the two prisms which he used to demonstrate optical tunneling using millimeter waves. So this is the entire electromagnetic spectrum. This I'm sure all of you know, from gamma rays to X-rays to ultraviolet to visible to radio waves that you receive on your cell phone. They are all electromagnetic waves, except that gamma rays have a very large frequency, then X-rays and radio waves have a frequency of the order of megahertz. But all wavelengths travel in free space, in vacuum, with an identical velocity, which is 299792458 meters per second. And that is now a universal constant. And the visible portion of light, visible portion of the electromagnetic spectrum, which goes from 0.4 micron to 0.7 micron wavelength, occupies a tiny region in the entire electromagnetic spectrum. So Max Planck had said that Maxwell's theory remains for all time one of the greatest triumphs of human intellectual endeavor. And in fact, Maxwell's theory explained almost everything, probably laws of reflection, laws of refraction, optical tunneling, properties of solids, and everything. So 1894, the famous British physicist Lord Kelvin said, there is nothing new to be discovered in physics now. All that remains is more and more precise measurement. And then in 1905, as all of you would know, Einstein, sitting isolated, like as Professor Lokanathan mentioned, that Isaac Newton's year of miracles was 1666, when sitting in his home, because there was plague in the United Kingdom, and Cambridge University was closed down. And there, sitting in his home in 18 incredible months, he produced tremendous results. He wrote a major part of his Principia and wrote the laws of motion and things like that. I'll not go into that. That is one full lecture itself. So in his year of miracles, when he was sitting isolated in the Swiss patent office, he would finish his patent work in the morning, and then he will work on his physics in the afternoon. That's the story goes. And he wrote 5 outstanding papers which changed the face of physics. And in the second paper in his year of miracles, Einstein wrote, radiation energy consists of indivisible quanta of energy. So he introduced the concept of the light quantum, which we today call as photons. And the photon, as you all know, will have the energy E is equal to h nu. And in a later paper, he said that the momentum was equal to h nu by c, where h is the Planck's constant, nu is the frequency, and c is the speed of light in free space. I thought I will just briefly mention the 5 papers where he introduced, he gave a theory of Brownian motion. He put forward the equation E is equal to mc square, and also wrote down the special theory of relativity, and gave a method for measuring molecular dimensions. So those were the 5 papers that changed the face of physics. So using his concept of the light quantum, he explained photoelectric effect, which, as you all know, if you have a cesium surface or a sodium surface, ultraviolet light falls, electrons are emitted. The maximum kinetic energy of the electron is equal to h nu minus a constant which depends on the property of the metal. This equation came to be known as Einstein equation, and which was verified with tremendous degree of accuracy by Robert Millikan around 1914. And because this was verified, so Einstein received the 1921 Nobel Prize in Physics. By then, general theory of relativity was also discovered by Albert Einstein, but not for his special or general theory of relativity, not even for the concept of the light quantum, not even for the concept of the photon, but for the explanation of the photoelectric effect. That Einstein got the 1921 Nobel Prize in 1922. So this medal, if you can see this, look at this very carefully, Einstein's name is mentioned. So this is the medal which Einstein received. And of course, Robert Millikan also got the 1923 Nobel Prize in Physics. And then after Einstein got the Nobel Prize, Arthur Compton did some beautiful scattering experiments in which a gamma ray photon hitting an electron gets scattered by it with a reduced energy, with a reduced frequency. And the certain energy is imparted to recoiling electron, and using simple kinematics, laws of conservation of momentum and energy, Arthur Compton derived that the wavelength of the scattered photon will be given by this, and which was experimentally verified by Compton in a set of very beautiful experiments. And only when Compton had done those beautiful experiments, people started believing in Einstein's light quantum. And this light quantum was named as a photon by an American chemist by the name of Gilbert Lewis. Arthur Compton received the 1927 Nobel Prize in Physics for his discovery of Compton scattering. And then, so this is the wave-particle duality, that light shows a wave nature through the experiments on diffraction and interference, and also a particle nature through experiments of Compton and photoelectric effect experiments. So the wave-particle duality was actually introduced by Einstein, because he had put forward the particle model of light. Then in 1897, J.J. Thomson discovered the electron. As you all know, today we know the mass of the electron to 10 decimal places. The charge of the electron also to 10 decimal places. It can be deflected by an electric or a magnetic field. So on the back of our mind, we think of electron as a tiny particle. Similarly, a proton, similarly a neutron, a tiny particle which can be moved here and there by means of an electric field. J.J. Thomson received the 1906 Nobel Prize in Physics. Then, as Professor Lokanathan mentioned, Louis de Broglie, in 1924, as a part of his doctoral thesis, said that this expression, P is equal to h by lambda, represents the momentum of a photon. So this expression should be also valid for electrons. So he predicted that. So once again, the wave-particle duality was discovered by Einstein. And Einstein, and what de Broglie said, that just as the light quantum demonstrates particle and wave nature, electron must also demonstrate a wave nature, and such that the wavelength of if an electron has a momentum p, it is associated with a wavelength lambda, which is equal to h by p. And he justified this from the Bohr's model. Niels Bohr had introduced this model in 1913, and he got the discrete orbits by introducing the quantization condition that the angular momentum mvr is a multiple of h by 2 pi. So he fiddled around with this equation, and he said, de Broglie said 2 pi r must be equal to nh by mv. mv is the momentum, so nh by p, n is an integer. So he justified the discrete Bohr orbits of Niels Bohr by saying that it corresponds to an integral number of wavelengths. And then I thought I will show you that Niels Bohr had come to Delhi University in 1959. I was much younger at that time. I was probably finishing up my MSc. And there is me, there is Professor R.P. Mitra of Chemistry Department, Professor F.C. Olak, who taught us mathematical physics, and Professor Majumdar and Professor Kothari were somewhere here. It was a great day. It was like a festival. And the whole hall was packed. And we listened to a very beautiful lecture by Niels Bohr. It was around end of 1959. So Niels Bohr received the 1922 Nobel Prize in Physics, and de Broglie received the 1929 Nobel Prize in Physics for his discovery of wave nature of electrons. So although the wave nature of electron was predicted in 1924, it was only in 1926 or 27 that in a set of beautiful experiments by Davison and Germer and G.P. Thomson, who is the son of J.J. Thomson, carried out beautiful experiments showing the wave nature of electrons. And those were the famous diffraction patterns. So here is a diffraction pattern produced by aluminum by an X-ray beam, which is a light beam of very large frequency, and produced by electrons. So you see the similarity between the two patterns. And so therefore, therefore both photons and electrons demonstrate wave and particle properties. So this is the wave particle duality. People say J.J. Thomson put forward the particle nature of the electron, and his son G.P. Thomson put forward the wave nature, experimentally demonstrated the wave nature of the electron. And Davison and Thomson and Germer missed out on the prize. So this always happens in awarding the Nobel Prize. Davison and Thomson shared the 1937 Nobel Prize in Physics for their experimental discovery of the diffraction of electrons by crystals. So now listen to this very carefully. Is the electron or a proton a wave or a particle? Now some books write that it is sometimes a wave, sometimes a particle. Some books write that it is a wave and a particle. The correct answer is very beautifully described by Richard Feynman. I thought if I said that myself, you will probably not believe me. Feynman writes, listen to this, they are neither waves nor particles. So this is Feynman giving his famous Caltech lectures on basic physics. So he writes that they are neither waves nor particles. So what are they? So you have still not answered the question that what is an electron or a wave? What is the electron? Is it a wave or a particle? The answer is it is neither a wave, so you should not ask such questions. So the electron or proton is described by the wave function psi. And what is this wave function psi? It is the solution of the Schrödinger equation. And what is the Schrödinger equation? Feynman again writes, where did we get that equation from? The answer is nowhere. It is not possible to derive it from anything you know. Schrödinger equation cannot be derived. So where did it come from? So Feynman writes it came out of the mind of Schrödinger. Isn't that beautiful? So therefore, you have to remember one thing, that the electrons or the protons or the photons, they are neither waves nor particles. And I described the electron by a wave function psi, which is the solution of the Schrödinger equation. And the Schrödinger equation cannot be derived. And Feynman says it came out of the mind of Schrödinger. Of course, there are heuristic arguments to get to the Schrödinger equation. And I will give you one such argument, which is far from rigorous. So many love the Schrödinger equation so much that they have painted the equation on them. Many have tattooed the equation on their body. If you go to the net, and you will see many people have this. So images of the Schrödinger equation on human body, if you write on YouTube, on Google, then you will get many such beautiful images where people have painted on their back and things like that. So I'll give you a very heuristic derivation. I assume a wave like the one that I had assumed in the very beginning of this lecture. So this is a displacement I describe by a plane wave using the exponential notation. Then I have the de Broglie relation, which is P is equal to h by lambda, h by 2 pi and 2 pi by lambda. So it is h cross k. So k is equal to P by h cross. And we also have the Einstein relation, that E is equal to h nu, which is equal to h cross omega. So omega is equal to A by h cross. So I substitute this here. I somehow introduce the particle nature in my wave function. So the wave function describes the electron. So I replace k by P by h cross and omega by E by h cross. Then for a free non-relativistic particle, the energy is given by P square by 2m. So therefore, the wave function which I had written down as I by h cross px minus et, this is what I had written down. So I replace E by P square by 2m and I get this. So this is a wave function describing a free electron or a free proton of mass m of momentum p. I differentiate this with respect to time and I get, if I multiply by I by IH cross, so IH cross times I by H cross is minus, 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 plus, H cross cancels out, P square by 2m times this whole thing. So it comes out to be P square by 2m side. I differentiate this twice with respect to x, so I get I by H cross P and square that minus P square by H cross square. So minus minus plus H cross square cancel out P square by 2m side. So the right hand sides are equal, and so therefore the left hand side will be equal, and I get one-dimensional time-dependent Schrodinger equation for a free particle. Now you do not ask me how I have got there. Each book has its own way of arriving at the Schrodinger equation. But somehow I have got this. I take it as a Bible and solve this equation. And the solutions of this equation agree with experiments, and that is the success of quantum mechanics. So, if the particle is in a potential field given by V of x, then the total energy is P square by 2m plus V of x. So you get the time-dependent Schrodinger equation for a particle one-dimensional in a potential field V of x. If instead of a one-dimensional wave, I had started with a three-dimensional wave, so this is k dot r minus omega t, that is kxx plus kyy plus kzz. So I replace by pxx, psy, pa by pzz. And I differentiate this with respect to x, with respect to y, with respect to z. Use the fact that E is equal to P square by 2m plus V of r, and I will end up that. So I have given you a very heuristic derivation of the Schrodinger equation. It is far from rigorous. But now I take this as the truth and solve this. A major portion of non-relativistic quantum mechanics is just the solution, whether it is the scattering theory problem or the bound state problem. It is a solution of the Schrodinger equation. And the validity and the fact that it got very readily accepted, and it is still accepted 100 years from the date it was discovered in 1926 by Schrodinger, quantum mechanics, is because its success. Of course, there have to be some refinements that have to be made. The spin of the electron has to be, the spin means that the electron behaves like a tiny magnet, and that leads to an interaction energy that has to be brought from outside. Although the relativistic theory does give the spin angular momentum of the electron. So in his 1926 paper, Schrodinger derived this equation. He used a completely different method of getting to this equation. And he solved this problem for the hydrogen atom problem. And he obtained the discrete energy level. That was the great success of Schrödinger equation in his 1926 paper. And from then onwards, Schrödinger equation has been applied to numerous situations. And he could explain the emission spectrum of hydrogen, which was also explained by Bohr's theory, but Bohr's theory had ad hoc assumptions, whereas this is the solution of a equation. Now let me concentrate on the solution for a free particle in one dimension. So you remember if I now solve this equation, and it is given in any book, by the method of separation of variables, I write it as a function of x times function of t, the variables separate out, and I will obtain this. In fact, I had used this equation to derive this. So P is the momentum. So this is the solution of the, so I forget everything. What I'm doing now is the following. Understand this. When I say understand this, I am talking to my BSc or MSc students. I know there are a large number of senior people there. This is very elementary. So I start with Schrödinger equation. And I assume V of x to be 0, so it's a free particle. And I obtain the solution. So I get the solution where P can be lying between minus infinity to plus infinity. So since P can lie between minus infinity to plus infinity, so the most general solution is the superposition of this. And I put 2 pi h cross here so that there is a normalization thing. So this forms what is known as a wave packet. Max Born in 1926 itself, for which he got the 1954. He had to wait for 30 years to get his Nobel Prize. Used the Schrödinger equation to deduce that psi squared dx is the probability of finding the electron between x and x plus dx. And this is the physical interpretation. AP squared dp is the probability of finding the x component of the momentum of the electron between p and p plus dp. Electron, proton, neutron, or whatever you can think of. So let us suppose at t equal to 0, it's a Gaussian wave packet. It's a normalized thing. So integral of px dx from minus infinity to plus infinity is 1. So it is located at time t equal to 0 within a distance of about sigma naught. So P of x dx represents the probability of finding the electron between x and x plus dx. So as I told you, psi of this is a wave packet. So I put t equal to 0. So I get t equal to 0. So this term goes off. Now I can determine if I know psi of x comma 0, I can determine A of p by using the inverse Fourier transform. This is a Fourier transform equation. So I do the inverse Fourier transform and I calculate A of p, and this is the momentum distribution function. A of p mod square dp is the probability of the momentum lying between p and p plus dp. So I calculate this and I substitute it here to study psi of x at a later time. So if I know psi of the wave function at time t equal to 0, I can evaluate the wave function by solving the Schrödinger equation. So this is the trick. So I first determine A of p if I know psi of x0 by carrying out this integral, and then substitute it here and carry out the integral to vanish psi of xt. So if psi of x comma 0 is this, as I had mentioned, then A of p square dp becomes this. You have to do this yourself. It is given in most of the books. So this is the probability distribution, position distribution function. It's a distribution. P of x, psi square does not represent the probability. Psi square times dx, it represents the probability of finding the particle between x and x plus dx. And apx square is not the probability. Apx square dpx represents the probability of finding the momentum of the particle between px and px plus dx. And if you plot that, then if the particle is localized within a distance sigma naught, then the probability distribution function is localized within a distance h cross by sigma naught. So if you localize, if sigma naught becomes smaller, then delta px becomes larger. So delta x times delta px is of the order of h cross. This is my uncertainty principle, which is contained in the solutions of the Schrödinger equation. So everything is contained in the Schrödinger equation. In 1927, Heisenberg gave the uncertainty principle. Many people feel that it is from top, but that is part of the solution, part of the Schrödinger equation. All solutions of Schrödinger equation are consistent with the uncertainty principle. So here, I have done this calculation myself. This is the wave function, the real part of the wave function at t equal to 0. In time t naught, it propagates to a distance. So it moves with a group velocity, and it is still localized within a distance sigma naught. This is slightly more than sigma naught, this is slightly more than sigma. This is how a wave packet propagates. It's like the electron coming out of a filament. So now consider the tunneling problem. You all must have done in your quantum mechanics course. A particle comes in, interacts with the potential, there is a reflection and a transmission. There is a reflection coefficient and a transmission coefficient. Now see this. A single electron is described by a wave packet, by this wave packet at t equal to 0. One electron. At a later time, there is a reflected part and a transmitted part. Now let us suppose the reflection coefficient is say 40%. So you will say if there are 1000 particles coming in, then about 400 will be reflected back, 600 will be transmitted. That is not the correct answer. That is not the correct answer. One electron coming in here at t equal to 0 at a later time, which is described by a wave packet which is localized here and here. So it is here as well as here. Sorry. It is here as well as here. So one single electron is described by a wave packet which is here and here. If you make a measurement, then it is either here or there. So suddenly, from being at both places, it collapses to being either in the reflected wave packet or in the transmitted wave packet. That is the beauty of quantum mechanics. Where will it collapse to? I don't know. No one knows. I can only give you a probability. So same thing is for a beam splitter. I have a single photon source. So I have one photon coming in, 1, 1, 1, 1. That is reflected by a beam splitter, which has 50% transmission, 50% reflection. So the wave packet that represents the single photon is reflected and transmitted. So if you say there are 1,000 photons, you will say that 500 will be reflected and 500 will be transmitted. That is not correct answer. A single photon is in the reflected beam as well as in the transmitted beam. But if you have a detector here, either this detector detects or this detector detects. The photon being in both the beams suddenly collapses to being either here or there. This collapse of the wave function is a unique property, unique characteristic of quantum mechanics. I did the single slit diffraction experiment, which you must have all done in the optics course. I have a plane wave coming in. It could be a light wave or an electron beam or something like that. It interacts with the slit, and you have this intensity distribution which is derived in every book on optics. Where beta is equal to pi, b is the width of the slit, sine theta is the angle of diffraction, and lambda. Now, if you now solve the Schrödinger equation, which is also done in many books, then the electron is localized within this distance, and you solve the Schrödinger equation as you did for the free particle, and you assume that this is my wave function, then you will obtain the probability that the x component of the momentum of the electron lies within px and px plus dpx is given. This is obtained by solving the Schrödinger equation. So I have this electron beam interacts with the slit. The slit imparts a momentum in the x direction. X is this vertical direction. So the probability that the x component of the momentum lies between px and px plus dpx is proportional to the intensity distribution as predicted by my classical wave theory. So therefore, the smaller the value of B, greater will be the diffraction. Greater will be the average momentum imparted to the momentum, to the electron. And that is my uncertainty principle. And so therefore, you have here that just before let us suppose there is an array of detectors here. Just before it is given by a wave function which is everywhere in the slit. And then the process of detection makes it collapse to one point. And to this collapse, I can associate a probability distribution. The probability that it will collapse between x and x plus dx is given by this. Classical mechanics is deterministic in nature. Quantum mechanics is probabilistic in nature. That is the essential difference between classical and quantum mechanics. So I do this double slit experiment, and in any optics book, you get this double slit interference pattern, and if you do the corresponding quantum mechanical calculation, then you will get a probability distribution that it interacts with the slit imparts a momentum in the x direction. This is a conservation of momentum. And the probability distribution is the same as the intensity distribution given by the simple wave optics result. So therefore, if you do the same experiment with the electron gun, this is again taken from the Feynman lectures. The electron is a tiny particle which has a mass, well-defined mass. It passes through, so you think that it will either pass through hole number 1 or hole number 2. So if hole number 1 is open, you get an intensity distribution like this. If hole number 2 is open, you get an intensity distribution like this. Now, you think that the electron has a mass, has a charge, it will either pass through hole number 1 or hole number 2. So if both holes are open, it will be the sum of the two. But this is not what you observe. You observe an interference pattern. And that can happen if the electron passes through both the holes simultaneously. How does the electron pass through both the holes simultaneously? That no one understands. At least I do not understand. Does it split into half and half? No, it does not. Because when I make a measurement, it will be either one electron or no electron. Feynman says in his famous messenger lecture, the electrons comes in lumps. Never you will observe half of an electron or quarter of an electron. It will be always one electron or no electron. And you explain that by a probability distribution. And there are many experiments which have been performed. This is supposed to be one of the most beautiful experiment in physics, the double slit interference pattern using electrons. This photograph I have taken from a paper by Tonomura. And this is the screen with 10 electrons, 100, 3,000, 20,000 and 70,000. So where will 10 electrons, there will be 10 spots there. Where will it land? No one can. One can only predict a probability distribution. Contained in this diagram is the basic essence of quantum theory. And therefore it is said to be the most beautiful experiment in physics. Dr. Pradeepta, my 1 hour is almost over. I am also tired. What do I do? I finish.
Sir, if you want, you can take 5 or 10 minutes.
All right, 5 minutes.
Oh.
You see, that is the whole difficulty of a webinar. Webinar, I do not know whether the students have fallen asleep or, or have gone back home or something like that. If you find that the students have fallen asleep, then you close your lecture. So in a webinar, you cannot do that. You do not see your audience. There may not be any audience left in the auditorium. Chalo, doesn't matter. Let me finish it. So this is an experiment, beautiful experiment, single photon experiment. The left photograph of a young girl corresponds to 3,000 photons, and this is of 28 million photons. So it is always you make a measurement. You see, quantized measurement. That is, you have, as Feynman says in his, you must go to YouTube and write Feynman messenger lectures. He gave a set of 6 beautiful lectures, messenger lectures at Cornell University in 1966. By that time I had left Cornell, and it was my great regret that I could not listen to those beautiful lectures. But today with technology, they are available on YouTube. I must have heard each of the lecture 4 or 5 times. They are so beautiful. So I will request all the students and teachers to go to YouTube and listen to the last lecture, lecture number 6 on probability and uncertainty. And he more or less uses the wave-particle duality and culminates with the probabilistic interpretation. And he says that the electrons or photons arrive in lumps. But in wave theory, the wave intensity can be as small as you like. But here you detect either one photon or no photon. So here you have 3,000 spots. Here you have 28 million spots. And they are governed by a probability distribution which is predicted by quantum mechanics and which is consistent with the uncertainty principle. So the most fundamental theory now available is probabilistic in form and not deterministic. David Bohm was widely considered one of the best quantum physicists of all times. This is someone has written, I forget the name, So that is why I refer to David Bohm's book as one of the classics. There will be no, in the 4 books that I mentioned by Richard Feynman, Dirac, Bohm, and Cohen-Tanuji, you will not find any error, nor any misleading statement. Even in our book with Professor Lokanathan, we have tried our best not to make any loose statements. In quantum mechanics, it is very easy to make a loose statement. So you must read the classics. In fact, Professor D.S. Kothari taught us from Dirac's book that you all must read, as was mentioned by Professor Lokanathan, from Dirac's book. So, electrons, these are Feynman's words from that lecture at Cornell, which you must all listen. Electrons do not behave just, these are his own words, like particles. They do not behave just like waves. Electrons in orbits are not somewhat like a cloud or fog of some sort surrounding the nucleus. It behaves like nothing that you have seen before. Well, there is one simplification, at least. Electrons behave exactly the same way as photons. And then he says, I think I can safely say that nobody understands quantum mechanics. He says that because how does the electron pass through both the holes? It is as simple as that. That to visualize is very difficult. Okay, let me tell you one more thing and then I will close. I will not go into the details because I have run out of time. You have a doubly refracting calcite crystal. And so, if you have a laser beam passing through calcite, it produces 2 polarized beams. Let me not go into the details of that. So, here is an experiment in which a calcium atom emits 2 photons. The polarization of one photon is at right angles to the polarization of the second photon. Now, you pass through an XY polarizer like the calcite crystal that I have shown, and you find this X polarized. One particle would thus immediately affect the other particle, wherever in the universe it may be. Einstein called this spooky action at a distance. So this led to entanglement and EPR paradox, maybe some other time. So let me come to the end of the lecture. I quote Bell's theorem, which I wanted to prove as one of the most profound discoveries since Copernicus. Bell delivered a death blow to the local realistic picture of the world. Many experiments have demonstrated that the predictions of quantum mechanics for entangled particles are fully correct. And the world is really as crazy as predicted by quantum mechanics. So Einstein in 1917, soon after his theory of stimulated emission, he said that for the rest of my life, I will study light. I will reflect on what light is. I will try to understand what light is. And just before his death, 4 years and before his death, he said, all the 50 years of conscious brooding have brought me no close to the answer to the question, what are light quanta? And that is the thing that Feynman says, that no one understands quantum mechanics. Of course, today every rascal thinks he knows the answer, but he is deluding himself. I'm just an old storyteller. I do not know what the truth may be. I tell you the tale as it was said to be. That is by Sir Walter Scott. Thank you for your attention. That's it, Dr. Pradipta. Pairs with itself. And similarly, when you do the beam splitter experiment using photons, he very beautifully writes, it interferes with itself to produce the interference pattern. So this is the crux of quantum mechanics. And beyond a certain point, there is no classical description of that. One person asked this question and he or she is quite right, that how does the wave function collapse? I don't know. I don't know. The electron being suddenly at two places, it collapses to one place. These are the things that one does not have a physical understanding. You just have to act. And so therefore, what do you mean by this statement? That the electron is neither a wave nor a particle, then what it is? It is described by a wave function, such that it can interfere with itself to produce a probability distribution. Something like that. These are difficult questions. You must all students must read the first two chapters of Feynman Lectures, Volume 3. You must. It's a beautiful exposition and it will try to answer these questions. And there is a very beautiful book by Anton Zeilinger, Dance of the Photon. Try to read that. Try to read that. And of course, the first few chapters, why the entire book by Dirac. So those are the homework that I like to give to all students. And
Sir, hello.
Yes.
Sir, one question from YouTube live streaming, Somo Sarkar. Quantum mechanics states that wave particle duality of light exists, while QED can explain phenomena like diffraction as shown by Feynman, considering particle nature. So can we say that this duality doesn't exist? Once more, sir.
Yes, once more.
Quantum mechanics states that wave particle duality of light exists, while QED can explain.
You see, let me answer that by this point, that wave particle duality, that the most important point that you have to understand is that it is neither a wave nor a particle. That is the most important thing. And therefore, elementary quantum mechanics tells us, and that is correct. The quantum mechanics, as quotation from Anton Zeilinger, who is supposed to be one of the outstanding quantum optics person today in the world, that it just makes crazy predictions, but it is true. And this collapse of the wave function, it is the thing that you must remember is that it is neither a wave nor a particle. Neither a wave nor a particle. And I rather not go into QED because that is entirely a different area. I think you have to find the truth yourself.
So, sir, another one.
That's enough. It's already 127.
Okay, sir. Just one more question that we should finish. That is, sir, Sumit Patra. Sir, another thing you just showed us, the optical tunneling through the two sets of prisms. Is there any conceptual connection with the tunneling effect in quantum mechanics, whatever we learn?
Oh, yes. Yeah.
And is there any specific measurement of spacing between two prisms for optical tunneling?
You see, optical tunneling that I had shown is a classical optics experiment. And there is no quantum mechanics there. There is no quantum mechanics there. A wave, when it hits a rarer medium, the corpuscular model says that it should undergo total internal reflection. So you solve the wave equation and you will find that a certain energy will tunnel through. And there is an evanescent wave that is there in that tiny layer. And smaller the width of the layer, greater is the tunneling. If the width is very large, then the tunneling energy is very small. So once again, this optical tunneling experiment that was first done by Jagannath Bose is a classical wave experiment. There's no quantum mechanics there. Now, you do this experiment with alpha particle. Now, alpha particle sees a potential barrier as if it sees a mountain for which the height is so high that it cannot climb up the mountain and go to the other side. So you use the Schrödinger wave mechanics. So that is how the quantum mechanics comes in. And you calculate the tunneling probability. So when you calculate the tunneling probability for the alpha particles to tunnel through the nucleus, then you solve the Schrödinger equation. And therefore, it is described by a wave function. And there, you require quantum mechanics to do that. There is one more experiment that I would like to tell you. Very simple experiment. Let us suppose this is a uranium solid. Uranium is a radioactive substance. Now, let us suppose there are 10,000 atoms. So let us suppose its half-life is actually millions of years, is 1 year, 1 day. So what does that say? That 10,000 atoms, out of that, about 5,000 will disintegrate in 1 day. In the remaining 1 day, in the second day, about 2,500, then 1,250, and so on, about. It may not be 1,250, it may be 1,200 or 1,245 or something like that. So you see, all atoms are identical. Some atoms may stay on for days without disintegrating, in the next minute. Which atom will disintegrate? I do not know. No one knows. Even God does not know. They are governed by the rules of probability. And that is the basic thing of quantum mechanics. So embedded in this radioactivity experiment is impregnated the concept of quantum mechanics. And quantum mechanics allows you to do the first principle calculation, to calculate the lifetime of the alpha particle. The average lifetime that the alpha particle will stay inside the nucleus. Something like that. Chalo.
So that's all for today.
Quantum entanglement. That's a very, very interesting topic. Very interesting topic. And I will treat me to lunch. So Dr. Pradipta, you owe me a lunch. Okay? Is this all right?
Okay, sir. This memorable lecture was especially helpful in building basic understanding and figuring out problems in quantum mechanics. I think viewers were at a standstill in their progress. We hope you can join us again in our future endeavors. We hope that we will get your consent wish for your long life,
Yes,
good health,
yes.
and also expect for further enlightening works in the fields of physics in future. So
Whatever you do, you have to do it quickly. I am very old now. Chalo, I'm very glad that you have organized the lecture. I have enjoyed giving this lecture, but there are only 100. You said that there are so many people who have registered, but now I see I just saw there are only 100 students now remaining. So that's all right for me.
Now 100 students, and many of them are in YouTube live streaming.
Oh,
YouTube live streaming. So not I, sir. Our team is there. Some of our members are working together. So
yes, congratulations to both of you.
Okay, sir. Thank you. And last but not the least, I extend my hearty thanks and gratitude to the participants, viewer, for patience hearing and for their hearty cooperation towards a successful webinar. Okay?
Yes.
Thank you all again. Okay, I here like to announce the end of the lecture series 1. Thank you all.